So let me start. This is a talk that is a sort of continuation of the talk of this morning by Professor Ruffini. I will enter a little more into the details of the model of this induced gravitational collapse of these binary progenitors leading to gamma ray bursts, especially on the case of the long gamma ray burst. So I'll give more details if I have time. I don't know how long I should speak. Is half an hour?
Yeah, on the program,
half an hour, okay. No, if I have time, I have 2 or 3 slides about dark matter. About if I will try, okay, to keep the time. Okay, so that's it. So it was introduced this morning, this binary scenario of gamma ray burst. So I will not enter into much details about that, but just to tell you why I hope that you can find the connection between this kind of talks and your field. Of course, in this model of gamma ray burst, these have to do with black holes of a stellar mass of about 3 solar mass. It has to do with physics of neutron stars, so it has to do with strong interactions. So it has to do with the evolution of stars, or with the way the stars cool and all these things. So, and you know that particle physics is in all this evolution of binaries. For example, we know that the neutrino magnetic moment can be constrained, for example, from the cooling of red giant stars. And the same this morning, for example, it was shown the slide with the constraints on the axion properties can come also from the evolution of stars. So we know from this morning talk that gamma ray burst, this explosion that can reach up to 10 to the 54 ergs of energy emission in few seconds. So they illuminate, they light or pass cone up to very high redshift of the order of 10. So we are speaking about systems which we see up to billion light years away. So they track and they illuminate, they give us information about the evolution of the universe and the evolution of stars. And so the physics, if by any chance we catch or we reach an understanding of the physics of neutron stars, then we can use them to put constraints also on particle physics. So I hope you can find this connection. So this was shown this morning. So starting from a binary system, so 2 massive stars that start to evolve. So one of the more massive star evolves first, so it means faster, and can reach the stage of supernova explosion, and there is a first supernova explosion in the system that forms a neutron star. Then the system, this neutron star with an ordinary star, continue to evolve. This system continue to evolve up to the point where the second star reaches a stage of supernova explosion. And at this stage, this neutron star companion can be very close to this star that is going to explode. What means short orbital period here? Close star. So we are speaking about periods of the order of minutes to hours, very close, where the neutron star around the companion can rotate, can go around with velocities of the order of thousands of kilometers per second. And this is the kind of system that we would like to simulate to the comprehension of gamma, to reach a comprehension of gamma ray burst. So in this explosion, we are more or less here, this second supernova explosion of this binary system. So this system up to this point has evolved for million years up to this point, okay, more or less, the order of 100 million years roughly. And so this system can lead to a different kind of outcomes as a function of the binary parameters: distance, masses of the initial stars, energy of the supernova explosion, and all the physical processes involved in this system. So there is a bifurcation, and Professor Ruffini recalled us this morning that this leads to a family, to a subclasses of possible gamma ray bursts. I will focus on this system here, so on the simulations of this, and how can this lead to these different systems. So the system is like this. This is a scheme. See, this is supernova explosion. At the center of the supernova, a neutron star, new neutron star is being formed at the center. Here there is a lot of neutrino emission, you know very well. And this is the expansion material, the external material of the neutron star, which start to expand and to be expelled. And then if the neutron star is close enough, then the accretion process that will be created into this neutron star will be very, very, very efficient. And then you have something like this. Here is this zoom of this region here inside the neutron star. This is just the gravitational capture region created to the neutron star. It depends on the mass of the neutron star and depends on essentially on the velocity of this material. So then this material starts to fall into the field of the neutron star and becomes denser and denser and denser and denser close to the star, up to the point when it reaches the star and is shocked onto the neutron star surface. Then it's a shock that settles at a certain equilibrium distance. And there, inside, near the surface of the neutron star, the systems reach conditions of density and temperature very efficient for neutrino emission. And we will show the dominant process of neutrino emission is electron-positron annihilation near the surface of the neutron star. But very, very efficient. Efficient in such a way that these neutrinos carry out most of the energy gains in this gravitational infall. Energies of the order of 10 to the 52, 10 to the 53 ergs. So this is the system we try to simulate, and this is the main, this is the historical, some of the historical papers about this. This is Seldovich and Ruffini and Wilson in 72 and 53, where it was already introduced this process of electron-positron annihilation leading to neutrino emission as very efficient process. In the case of Seldovich, in the case of supernova, and in the case of Ruffini and Wilson was introduced as a possible explanation for ultraluminous X-ray sources. So here, then we jump to our paper, almost six years ago, when we made just the first a simple estimate of this process for this kind of system to explain gamma ray bursts. And then from this simple estimate, we reach the conclusion that the collapse, this accretion process onto the neutron star can be such that the neutron star could reach the critical mass for gravitational collapse and become a black hole. And so then we start to simulate. Okay, so I'm speaking about these two possible. These are the 7 families of GRBs Professor Ruffini introduced this morning. I will focus only on these two, where you have the supernova exploding near the neutron star, and then 2 possible outcomes. If the accretion process is efficient enough, then you can form a black hole. The neutron star companion can become a black hole. If not, then you just form a 2 neutron star system. Then these are some numbers of the observational properties of this system, so that the energies can reach up to 10 to the 54 ergs in the case when you form a black hole. Instead, when you don't form a black hole, the energies the system is less energetic, and we have a maximum energy of the order of 10 to the 52 erg in these cases. So how we start a simulation? So we use first conditions for supernova explosion for the supernova code of Los Alamos and in New Mexico. And this gives us initial conditions of the explosion of the supernova. We need density profile, we need velocity profile, and from this, we create initial conditions on the accretion process onto the neutron star companion. In our first simulations, these were in 2014, this was a one-dimensional code, one-dimensional approximation. It was actually very simple with respect to what we have now. But we here already see, we estimated the accretion rate onto the star, onto the nearby neutron star, and we reach, look here, up to of the order of 0.1 solar masses per second. This is a huge accretion process, thanks to the emission of neutrinos. So just roughly, if you just translate this into luminosity, this means that the neutrinos carry out about 10 to the 52 ergs per second of energy from this system. So a huge flux of neutrinos. These are MeV neutrinos because they are created by electron-positron annihilation with temperature between 1 and 10 MeV. Okay, so we saw this in this article here, and then we start to move after to include more and more effects, because in this first simulation we did not take into account the fact of the orbital motion of the star. So we start to introduce also the effect of the orbital motion of the angular momentum that the matter can reach near the neutron star. So this was our first simulation of this process. In 2015, we made some approximations again, just to have an idea what is going on inside this system and near the neutron star. Then we estimate that there is enough angular momentum such that when the matter reaches the vicinity of the neutron star, it actually do not fall directly into the star, but circulates around the star, and eventually it loses energy and goes and accretes into the star. This was our first estimate about that process, and this was a first simulation of that. Here you have the material expanding. This is the neutron star going around. You have here two different orbital periods. P0 is about 5 minutes. Here is an orbital period of 20 minutes, roughly. And here you have the star, the neutron star going around, and this gray ball is the gravitational capture region of the star. And you see here, this is a velocity field when you see the accretion process into the star. We confirm here that the neutron star could reach the critical mass for gravitational collapse. And then we start to go farther and to release some of these approximations that we made that we applied in the computation of this system, and went to a more sophisticated simulation here, just by assuming, just taking the initial conditions of the supernova code of Los Alamos and just applying this smooth particle hydrodynamics technique and divide the supernova material in several pieces, in such particles, let's say particles, quotation marks, and follow the evolution of all these pieces in the field of the nearby neutron star. Okay? This is a different approach. It's more sophisticated. These simulations is very time-consuming the computer. This is for 16 million particles in these simulations we use in our computer in ROM. So we were using our computer in ROM to do this. So it was, actually we don't have a huge computer. It's only a computer with 64 cores, and there we have to wait 15 days for one simulation only. So it was very difficult to explore the parameters space of this, but still we could, one, confirm of previous results, and second, to go further into explore this parameter space, even if little, with respect to what we have now. So this is the supernova explosion again. Here starts the accretion process onto this, the neutron star companion. Here we have some properties that we get nearby in the flux of neutrinos near the neutron star surface. Here you have some numbers as a function of the accretion rate onto the neutron star. You have density of the matter nearby, near the surface of the neutron star, temperatures, the electron-positron density, then the energy, mean energy of the neutrinos. You see here from 6 to 30 MeV, and here the fluxes. So you can see here, look at the luminosity of neutrinos. So between 10 to the 48 to 10 to the 57 MeV per second. This is the range, correspond to this range of accretion rate where we have in this system. So some of these details of this neutrino physics, it was published this year here, where we just compute also the evolution of these neutrinos, escaping from the system and interacting also with matter, and introducing also self-interactions of neutrinos to look at the possible processes of neutrino oscillations. So these are some of the results. Look at here temperature and density near the neutron star, and you can see here this line here just give us the conditions of our system for the accretion rates we expect in this system. Here is from 10 to the minus 8 solar masses per second. Here is 10 to the minus 2 solar masses per second. Here you move from the less energetic to the most energetic systems. And all of them you can see here, these are the process of neutrino emission. They are all dominated by electron-positron annihilation, all of them. And here, okay, this is just the neutrino spectrum. Let's go farther. What is the problem here? Then, to decide, we have to decide when the neutron star reaches the point of gravitational collapse. This is a key issue. So when we compute just the flux reaching the neutron star gravitational capture region, this is about 100 times the radius of a neutron star. So in this first part of the simulation, we can treat the neutron star just a point mass. But then when we look at the physics nearby the star, we cannot do that. So we have to introduce general relativistic effects near the neutron star. So at each point, when we launch these baryons into the star, then we have, and these baryons and this angular momentum that the star receives, we have to compute how the neutron star reacts to this in terms of its gravitational mass. So we have to compute the evolution of the gravitational mass of the star and then decide if the star reaches a point of instability at some point of its evolution. So we have to, these are just Einstein equations for the axisymmetric case, which we have to solve at each point of this time of the simulation. We know the mass, angular momentum that is transferred to the star, and then at each time we know how the mass of the star increases and how its angular momentum increases. Then we do this coupled system of equations, a lot of stuff, but at the end we manage to do it, and then when we see something like this is the accretion rate. This is the difference between baryon mass accretion rate and the actual the gravitational mass accretion rate onto the star, how the star increases its mass. Here you see, does it mean this is mass versus central density of the neutron star. So you have a star starting somewhere here, initial conditions of the neutron star. You see how the stars evolve inside this plane. What is here? These are all the stable, possible stable rotating neutron stars. So you have two limits of equilibrium. One here is mass shedding limit or Keplerian limit. So the maximally rotating neutron star limit here, okay? And here you have the secular instability, secular axisymmetric instability, where the star is unstable with respect to oscillations. And it's actually this limit here which defines the critical mass for gravitational collapse of the star. So if this neutron star reaches at some stage of its evolution, this line, it means that it's going to form a black hole. This is the point of gravitational collapse. So actually we see here, what you see here are possible actually evolutionary paths inside this process of accretion. So these are results of real simulation, this kind of evolution, where you can see actually that the star reaches the point of gravitational collapse to a black hole. And this happens depending on the binary period. It can happen in 50 seconds, in 100 seconds, in 1,000 seconds. Okay, here is, well, this is just the critical mass. This is a fit of this line. Just this is useful to have these fits of this, and these properties of the star to make the computations faster. And you can see here it can reach up to 3 solar masses. It depends, of course, of the equation of a state of a neutron star. And here, this our first spherical supernova explosion, how it becomes very, very asymmetric, very, very asymmetric because of the presence of this neutron star nearby. This is the point at which a neutron star reached the point of gravitational collapse to a black hole. The neutron star is here. This was the center of the supernova explosion. So here there is a neutron star, and here as a black hole is formed at this moment. And this is an example of a system with an orbital period of 50 minutes in which the neutron star does not reach the point of gravitational collapse. These are two different. But still, also in this system, you can see the asymmetries that are created in the supernova ejecta, in this supernova material that is expanding because of the neutron star expansion. And we actually have, in our analysis of data or GRBs, actually the effects of these asymmetries that are created into the supernova actually can be observed. Professor Ruffini showed this morning in the data of X-ray flares. We have also in the data of the other system, the X-ray flashes, actually evidence of these asymmetries. So here, just simple accretion rate. This is the peak accretion rate, time at which you reach a peak accretion rate. This is the orbital period. And you see, this is an example in which you separate these systems from up to this period, to this orbital period. These systems form a black hole by accretion. And in these systems, you don't. So we have these separate families. So in this system, where you form a black hole, we call these binary-driven hypernovae. And in these cases, we call them X-ray flashes. So this is a summary of this system. We analyze as well that these binaries, these ones, forming a black hole, actually most of them are going to keep bound when this explosion happens. So actually, by this mechanism, you form, from this initial system, you form neutron star black hole binaries. And in the other cases, oh, sorry. Yes, in these binaries here, they are far apart. Not all of them are kept bound after the explosion. Most of them actually are disrupted by the explosion, and some of them keep bound. So we have this data from our simulations too. And so we have actually a connection between this mechanism that is for long gamma ray bars as a source of binaries, of compact star binaries that are at the same time, in due time, sources of short gamma ray bars in the coalescence, in the merger process of neutron star black hole or neutron star, neutron star. So this is okay. This is the three-dimensional picture just to show you how it looks at the moment of collapse. These are our first simulations. And then, I don't know how long I can speak now. Oh, okay. So we have just more sophisticated simulations, semi-initial conditions, but now a new smooth particle hydrodynamics code that we developed together with Los Alamos. So it was we adapt the code that they have for single explosion, single star explosion. We adapt to binary, and it was done recently. So it's new SPH code, and now we have more efficient process, less time consuming too. Now we run at Los Alamos only one night to have one result, one simulation, so this is good. And now we are really exploring all the parameter space of this system. And now we have only, instead of using 16 million particles, we reduce to 1 or 2 million particles. It's much more efficient, this system. And we have essentially this new code. The results are the same, roughly from the physical point of view, the same. But the only difference is that we now are able to explore all the parameter space easily. So from different masses, from different binary, from different initial masses, different explosion energies, different binary separations, we can make all this study. This is new. This is going to be published. And therefore, here the interconnection that I was speaking now before, long GRBs that become sources of short GRBs because become sources of compact star binaries. This is the interconnection that is confirmed from our latest simulation. And of course, you can estimate the gravitational waves from these latest systems. So you form from these neutron star, or neutron star black hole binaries that are good candidates in principle for detection of gravitational waves. So you can estimate, go further. This was recent paper just appearing this month in journal in JCAP, both or simulations of these kind of binaries. But then going further from this, I have not very much time for this. Okay, this is our results for GRBs. So actually, we were estimating if LIGO, with advanced LIGO and all the detectors could actually detect these gravitational waves from neutron star, and neutron star black hole binaries that from the data of GRBs. Okay, this is based on the data of GRBs, from known GRBs. So from known distances, from known occurrence rate of GRBs is computed. So our results was, answer is no, was our answer. From this, best case of possible observation was the case of the binaries, neutron star leading to neutron star. So not leading to a black hole in the merger. And we expect this from the new observation run of advanced LIGO, we expect that was something like one source every 20 years or so. This was based on the occurrence rate, density rate of GRBs we know today. Okay, okay. This was about extra slides, different topic, but just to touch the point, okay? Just give me just 1 minute, okay, about this topic. Because we have heard about fermions as possible candidates of dark matter. Okay? So we have been working on this topic also already from some years, estimating to computing what would be the distribution of fermions of this possible dark matter candidate in a galaxy. Okay? So we have This is a general view of the galaxy. You have the galaxy core and the dark matter halo. You all know, you are familiar with the problem of rotation curves and why we introduced dark matter this. I don't need to recall this to you. So I go directly to the point. So this is paper of 2015 when we introduced what we call the RAR model, R-A-R, so Ruffiner-Weijes-Rueda model, of this distribution of fermions in the galaxy. So how these fermions would distribute. Actually, so we're assuming a fermion gas, what we obtain after introducing equation of self-gravitating system in general relativity, what you obtain is something like this. Okay, this is the plot that I would like to call your attention. Okay, these are the rotation curves, so the velocity of the stars in the galaxy, the head of the galaxy, and these are the density, dark matter, the fermion density profile that you get inside the galaxy. So what you get here? You have here the blue points are the data of the velocities. What happened here? So what is happening is that each of these profiles that has each profile has an associated fermion mass and different conditions of temperature and degeneracy of these fermions. And each of them is leading to contribute differently to the rotation curves, to the theoretical rotation curves. What you can see is that for some masses, some fermion masses are excluded from the data because they would induce a too large velocity of the stars, and you don't see that. These are, for example, the case of this yellow, of this red cube here. From this analysis, we get a lower bound to the fermion mass, and this lower bound is about 10 keV. So it's a lower bound. And then, if you go further with this idea, since you see that you get a high density near the center of the galaxy, then we explore the possibility, and what if these fermions, if this core of high density can make the work of the central black hole, of the hypothetical central black hole in the galaxy, okay? We just make this possibility, okay, because this is a real possibility. Because what we know from the center of the galaxy is that there is an object of 4 million solar masses, and that this mass is estimated from the motion of this cluster of stars, the S cluster. And then, but the closest star to the center of galaxy is about 1,000 Schwarzschild radii. So actually, there is still ample room. If you have an object of that mass inside that radius, then you make the work, okay? So this is exactly what we show here. And from this, in order that if you impose from these fermions to explain these stars and this rotation curve here, then you get also an upper bound to the mass of 350 keV. So we have from 10 keV to 350 keV for fermions. But if you go to other type of galaxy, this is from the Milky Way, then we are reaching to a conclusion that possibly, very likely, the mass, the good mass is of the order of 50 keV. This is what I can tell you. You can see more details here. This here is the reference. Oh, sorry, I'm very sorry. That's all.